Welcome to Still Science Lab. Tonight, we are going to ask a question that sounds like it belongs in a kindergarten classroom, but which actually breaks the machinery of modern physics. It is a question that seems simple on its surface, yet the moment you try to answer it, the ground beneath your feet begins to dissolve. We are going to look at the light streaming from your lamp, or the glow of this screen, and we are going to ask, what is a photon made of? When we ask what something is made of, we are usually asking for a list of ingredients. If I hand you a loaf of bread, you can tell me it is made of flour, water, yeast, and salt. If I hand you a rock, you can tell me it is made of minerals like quartz and feldspar. If we zoom in with a powerful microscope, we can say those minerals are made of molecules, and those molecules are made of atoms. We can keep playing this game of cosmic nesting dolls. The atom is made of a nucleus and electrons. The nucleus is made of protons and neutrons. Even the protons and neutrons are made of something smaller, quarks held together by gluons. We are conditioned to believe that reality is a construction project, built from smaller and smaller bricks. We expect that if we look closely enough at anything in the universe, we will find its internal gears. But then we get to the photon. We catch a particle of light, we hold it under the metaphorical magnifying glass, and we ask, what are your parts? And the universe gives us a terrifying answer. It doesn't have any. This is the central paradox we are going to explore. A photon is not a composite object. It is not a bag of smaller particles tied together by string. As far as we know, it is a fundamental unit of reality. It has no size, no radius, and no internal structure. It is a point. But how can a point, a zero-dimensional speck of nothing, carry the energy to warm the Earth? How can something with no mass push a solar sail? How can something that isn't made of anything be the most visible thing in the universe? To answer these questions, we have to unlearn almost everything our intuition tells us about the nature of stuff. We have to stop thinking of matter as frozen chunks of reality and start thinking about fields, vibrations, and the geometry of space-time itself. To understand why this question is so difficult, we have to go back to the moment human beings first realized that light was something that could be quantified. For most of history, light was just a condition of the environment. It was either day or night. But in the 17th century, Isaac Newton decided that light must be a stream of tiny bullets. He called them corpuscles. In Newton's mind, if you stared at a candle, your eye was being bombarded by millions of tiny, invisible rocks. This made sense. It fit with the mechanical view of the world. If light bounces off a mirror, it is just like a tennis ball bouncing off a wall. It has momentum, it travels in straight lines, and it hits things. If Newton were right, the question, what is a photon made of, would be easy. It would be made of corpuscle stuff, just a tiny nugget of matter. But Newton was wrong. Or, at least, he was only half right. Around the same time, Christian Huygens argued that light was a wave, like a ripple moving through water. This started a war in physics that lasted for 200 years. If light is a wave, the question changes. A wave isn't a thing in the same way a rock is a thing. You cannot hold a wave in your hand without the water. A wave is a behavior. It is a disturbance traveling through a medium. If light is a wave, then a photon isn't a particle at all. It is just a vibration. But a vibration of what? Sound is a vibration of air. Ocean waves are vibrations of water. If light is a wave traveling from the sun to the earth through the empty vacuum of space, what is waving? This led scientists to invent the luminiferous ether. a ghostly substance that was supposed to fill the entire universe just so light would have something to travel through. They wanted light to be made of ether vibrations. But the ether didn't exist. We looked for it, and it wasn't there. So we were left with a wave that travels through nothing, a ripple in a void. Then, at the start of the 20th century, Albert Einstein came along and broke the world again. He looked at the photoelectric effect, the way light knocks electrons off a metal plate, and realized that waves couldn't explain it. The light was hitting the metal like a hail of bullets. It was arriving in discrete packets of energy. He called them quanta. We later called them photons. Einstein forced us to accept a reality that makes no intuitive sense. Light is both a wave and a particle. It propagates like a ripple, but it hits like a bullet. This duality is where our question, what is a photon made of, hits a brick wall. If it is a particle, it has no mass. An electron has mass, you can weigh it. A proton has mass. But a photon has zero rest mass. If you could stop a photon and put it on a scale, it would not exist. A photon is its motion. It exists only because it is moving at the speed of light. The moment it stops, it is absorbed and vanishes. So, we are talking about an object that has no mass, no internal parts, no size, and cannot exist at rest. It sounds less like a physical object and more like a ghost. Yet, we know it is real. We know because it carries energy. It carries momentum. When sunlight hits your face, you feel the heat. That heat is energy being transferred from the photon to the atoms in your skin. If the photon has no mass, where is it hiding that energy? In a baseball, the energy is in the mass and the speed. In a photon, the energy is entirely in the frequency. It is the color of the light that determines how hard it punches. Blue light punches harder than red light. X-rays punch harder than blue light. This suggests that the stuff of a photon is not matter, but pure periodicity. It is a packet of rhythm. So, are we satisfied with the answer that a photon is made of energy? Not really. Energy is a property, not a substance. You don't have a cup of pure energy any more than you have a cup of pure tall or pure fast. You have energy of something. The energy must belong to a substrate. We are missing the noun. We have the adjectives fast, energetic, electromagnetic, oscillating, but we are missing the noun that those adjectives describe. What is the noun? The search for that noun will take us out of the world of classical mechanics and into the strange, hallucinatory landscape of quantum field theory. We are going to find that the universe is not made of particles at all. It is made of fields vast, invisible oceans of potential that span the entire cosmos. We are going to learn that a photon is not a tiny marble flicked by a god. It is a localized excitation of the electromagnetic field. It is a snap in the fabric of space-time. It is a quantum. But even that word quantum is a mask for a deeper mystery. Over the next 9 parts of this series, we are going to dissect this ghost. We will look at the anatomy of a gauge boson. We will ask how a photon can spin if it has no surface to spin. We will ask how it can interact with electrons if it has no charge. We will explore the idea that light might be the only thing that is truly real, and that matter, the stuff we are made of, is just light that has been trapped in a box. We are going to peel back the layers of reality until we are staring at the raw code of the universe. Tonight, we start by acknowledging that our language fails us, our common sense fails us. When we ask, what is a photon made of? We are asking a question that implies the rules of the playground apply to the rules of the quantum realm. They do not. But that doesn't mean there isn't an answer. It just means the answer is going to require us to redefine what it means to be. The photon is the bridge between the void and the material world. It is the messenger particle. But a messenger implies a message. What is the message? And what is the paper it is written on? To find out, we have to stop looking at the light and start looking into it. We have to dive into the wave function. We have to confront the vacuum, and we have to accept that in the world of light, the only thing that is solid is the math. Let us begin our descent into the light. To understand what a photon is made of, we must first understand the centuries-long identity crisis that light has suffered. Before we could even ask about the quantum nature of the photon, we had to decide if light was a thing or an action. This distinction is crucial. A rock is a thing. It has boundaries and substance. A shout is an action. It is a disturbance moving through the air. For thousands of years, humanity looked at the sun and the stars and couldn't decide which category light belonged to. The ancient Greeks argued about it, with some believing that beams of fire shot out of our eyes to touch the world, tactile feelers of vision, while others believed the world shed skins of atoms that flew into our eyes. But the debate didn't truly become a scientific war until the age of Isaac Newton. Newton, the titan of classical physics, was a staunch believer in the thing theory. In his view, light had to be made of particles. He called them corpuscles, a word that brings to mind tiny biological cells or blood, but he meant it in the sense of small, discrete bodies. His logic was grounded in the harsh geometry of the shadow. If you stand in the sunlight and someone builds a wall in front of you, the shadow is sharp. The light stops exactly where the wall begins. If light were a wave, Newton argued, it should behave like sound. When someone speaks around a corner, you can still hear them because the sound waves bend or diffract around the obstacle. Light doesn't seem to do that. It travels in strictly straight lines, like bullets fired from a gun. Therefore, light must be a stream of microscopic bullets. For over 100 years, because Newton was the smartest man who ever lived, science accepted that light was made of corpuscle stuff, tiny pellets of matter. But nature is not a democracy, and it does not respect the authority of geniuses. In the early 1800s, a polymath named Thomas Young performed an experiment that shattered Newton's bullet theory. He set up a simple barrier with two narrow slits cut into it and shone a light through them onto a back screen. If light were made of bullets, you would expect to see two bright strips on the back screen directly behind the slits where the bullets passed through. But Young didn't see two strips. He saw a complex pattern of bright and dark bands, a series of zebra stripes stretching out to the sides. This was an interference pattern. It is the exact same thing you see if you drop two stones into a pond at the same time. The ripples from one stone meet the ripples from the other. Where two crests meet, the water goes higher. Where a crest meets a trough, they cancel each other out and the water goes flat. Young's experiment proved that light was doing something that bullets could never do. It was adding itself to create zero. Light plus light was equaling darkness. This was the death knell for the corpuscle. You cannot take two rocks, smash them together, and have them vanish. But waves do that all the time. The scientific community swung violently to the other side. Light was not a thing, it was an action, it was a wave. But this victory brought back the original haunting question. A wave of what? If light is a ripple, what is the water? This is where the story introduces the greatest fictional substance in the history of science, the luminiferous ether. Scientists reasoned that if light is a wave traveling from the distant stars to our eyes, the vacuum of space cannot be empty. It must be filled with a medium. Sound waves need air. Ocean waves need water. Seismic waves need the earth. You cannot have a vibration without a vibrator. So, they invented the ether. It had to be a miraculous substance. It had to be invisible, tasteless, and frictionless, so that planets could orbit through it without slowing down. Yet, it also had to be incredibly stiff. The speed of a wave depends on the stiffness of the medium. Sound travels faster in steel than in air because steel is stiffer. Since light travels at a blistering 300,000 kilometers per second, the ether had to be millions of times more rigid than steel, yet lighter than the thinnest gas. It was a paradox, but it was the only way to explain what light was made of. In the 19th century view, a photon was just a stress wave propagating through this invisible cosmic steel. Then came James Clerk Maxwell, the man who would inadvertently write the instruction manual for the modern world. Maxwell wasn't looking for the Aether, he was playing with electricity and magnetism. At the time, these were seen as separate oddities. Electricity was sparks and currents. Magnetism was compass needles and lodestones. Maxwell unified them with a set of 4 elegant equations. He showed that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. They could leapfrog over each other, creating a self-sustaining chain reaction that would travel through space. When Maxwell calculated the speed of this theoretical electromagnetic chain reaction, the number that popped out of his equation was exactly the speed of light. It was a revelation. Light was not a mechanical wave pushing against a physical ether. It was an oscillation of fields. It was electricity and magnetism dancing together. This gave us a new answer to our question. What is a photon made of? It is made of fields. Specifically, it is a transverse wave where the electric field pushes up and down, and the magnetic field pushes left and right, and the whole bundle shoots forward. This seemed to settle the matter. We didn't need bullets. We barely even needed the ether anymore, though people clung to it for a few more decades. We had a beautiful, continuous, wave-like description of reality. But as the 19th century turned into the 20th, the wave theory began to rot from the inside. The problem was that if light were purely a continuous wave, the universe should not exist. This catastrophe emerged when physicists tried to calculate the color of light coming from a hot object, like a toaster filament or a star. According to the wave equations, a hot object should radiate an infinite amount of energy in the ultraviolet part of the spectrum. Every time you turned on your oven, it should blast you with enough high-energy radiation to fry the entire solar system. This was called the ultraviolet catastrophe. The math of the wave said infinite energy, but reality said nice warm toast. Something was fundamentally broken in our understanding of what light was made of. The wave theory assumed that energy was continuous, that you could have any amount of light you wanted, just like you can pour any amount of water from a bucket. You can pour a gallon, or a cup, or a drop, or a billionth of a drop. But nature was whispering a different rule. Nature was saying that light wasn't like water, it was like sand. You can have 1 grain of sand, or 2, but you cannot have half a grain. You cannot have a continuous flow, you can only have chunks. This leads us to the precipice of the quantum revolution. We had abandoned Newton's particles because of the double slit experiment. We had embraced Maxwell's waves because of the beauty of electromagnetism. But the waves were predicting impossibilities. We were stuck in a trap. If light is a particle, it can't interfere. If light is a wave, it destroys the universe with infinite energy. We needed a new concept, something that could reconcile the math of the continuous field with the reality of discrete impact. We needed to rediscover the particle, but not as a Newton bullet. We needed to discover the quantum. To solve this, a reluctant physicist named Max Planck had to do something he hated. He had to break the laws of physics. He guessed purely as a mathematical trick to make the equations work, that energy could only be absorbed or emitted in tiny, discrete packets. He didn't believe it was real. He thought it was just a bookkeeping convenience. He called these packets quanta. He assumed that eventually someone would find the real continuous theory. But he was wrong. The packets were real. The granularity was real. The smooth beam of light was actually a hail of machine gun fire. And so, we arrive at the dawn of the 20th century with a schizophrenic answer to our question. We have a phenomenon that travels like a wave of oscillating electric and magnetic fields, filling the room, bending around obstacles, and interfering with itself. But when it hits the wall, or your eye, or a camera sensor, it lands as a single, localized point of energy. It travels as a ghost and hits like a brick. This is the birth of the photon as we know it today. But knowing that it is a packet of energy is not the same as knowing what it is made of. If it's a packet of field, how does a field ball itself up? How does a wave become a dot? To understand that, we have to go deeper than classical fields. We have to enter the world of relativity. We have to ask what happens to this wave when it moves at the universal speed limit, where time stops and space contracts to zero. We are about to find out that a photon is a particle that experiences no time and traverses no distance. It is a connection between 2 points in the universe that, from the photon's perspective, are the same point. We left the last segment standing on the edge of a paradox. We had a wave theory of light that worked beautifully for explaining how light moves through space, bending around corners and interfering with itself like ripples in a pond. But that same theory predicted that your toaster should blast you with lethal X-rays every morning, a mathematical absurdity known as the ultraviolet catastrophe. The world of physics was waiting for a savior, or perhaps a revolutionary, to bridge the gap between the smooth, continuous math of waves and the jagged, discrete reality of matter. That revolution arrived in 1905, not from a prestigious professor in a grand university, but from a 26-year-old patent clerk in Bern, Switzerland, named Albert Einstein. He was about to take the quantum idea, which Max Planck had used merely as a mathematical bandage, and turn it into a physical reality. In doing so, he would finally give us the first real answer to what a photon is. It is not just a ripple in the aether. It is a bullet of pure action. Einstein turned his attention to a phenomenon that had been annoying experimentalists for years: the photoelectric effect. If you shine a light onto a clean metal surface, the light can knock electrons loose, creating a small electric current. This makes sense even in the wave theory. The light carries energy, and if you dump enough energy into the metal, the electrons should eventually shake loose, like apples falling from a tree in a storm. But when physicists looked closer, the details didn't add up. According to the wave theory, the brightness, intensity of the light should matter most. A brighter light is a bigger wave, striking the metal with more force. Therefore, a very bright red light should easily knock off electrons, while a dim blue light should struggle. Furthermore, there should be a delay. If the light is dim, the electron should have to soak up the energy for a while before it has enough to escape. But the experiments showed the exact opposite. A bright red light, no matter how intense, could shine on the metal for 100 years and not a single electron would budge. Yet, the moment you turned on even the faintest, dimmest blue light, electrons popped off instantly. It was as if you were throwing millions of ping-pong balls at a brick wall and nothing happened, but then you threw a single pebble and the wall shattered. The wave theory had no explanation for this. It predicted that energy depended on amplitude, brightness, but nature was shouting that energy depended on frequency, color. Einstein realized that there was only one way to explain this. Light was not hitting the metal like a continuous stream of water. It was hitting it like a hail of discrete projectiles. He proposed that the energy of light is not spread out evenly over the wave, but is concentrated in tiny bundles. He took Planck's mathematical trick E equals hf and applied it to the light itself. The energy E of each bundle is equal to a constant h times its frequency. This simple equation changed the world. It meant that a red photon has a low frequency and therefore carries very little energy. It is a soft bullet. You can fire 1 billion of them, high intensity, but each individual bullet is too weak to knock the electron loose. It's like throwing 1 million marshmallows at a window. The window won't break. But a blue photon has a high frequency. It packs a hard punch. Even a single blue photon, low intensity, has enough energy in its individual packet to knock an electron free. It is a rock thrown at the window. This was the birth of the photon as a particle. Einstein didn't call them photons, yet that name came later from a chemist named Gilbert Lewis, but he had defined their nature. A photon is a quantum of electromagnetic action. It is the fundamental unit of light. This solved the ultraviolet catastrophe because it meant you couldn't just emit infinite energy at high frequencies. High-frequency photons cost a lot of energy to create. Nature can't afford to make trillions of X-ray photons in your toaster, so the curve drops off and the universe is safe. But solving one problem created another, deeper mystery. If the photon is a particle, a thing that punches electrons, it must have mass, right? A bullet has mass, a rock has mass. Momentum, the ability to push things, is classically defined as mass times velocity, p equals mv. If a photon has no mass, it should have no momentum. It should be a ghost that passes through matter without touching it. But we know light pushes things. We know comet tails point away from the sun because sunlight pushes the dust. We know solar sails work, so we are faced with a contradiction. How can a particle with zero mass have a physical impact? To answer this, we have to look at what mass actually is. In our daily lives, we think of mass as heaviness, or the amount of stuff. But in physics, there are two kinds of mass. There is rest mass, the mass an object has when it is sitting still on a table. And there is relativistic mass, the apparent heaviness an object gains when it moves. Einstein's special relativity tells us that energy and mass are interchangeable. E equals m2. As you push an object faster, you add energy to it, which effectively acts like mass. But the photon is unique. It has zero rest mass. If you could trap a photon in a box and stop it dead, it would weigh nothing. In fact, it would cease to exist. A photon is defined by its motion. It exists only at the speed of light. Because it moves at c, the speed of light, the photon bypasses the old Newtonian rule of momentum. For a photon, momentum doesn't come from mass, it comes from frequency. The momentum of a photon is simply its energy divided by its speed, p equals E divided by c. This is why it can push a solar sail. It doesn't need to be heavy, it just needs to be energetic. It transfers its momentum not by smashing a heavy weight into you, but by transferring its electromagnetic state to your atoms. It is a kick of pure field energy. This brings us to the most mind-bending aspect of what a photon is made of. Because it has no rest mass and travels at the speed of light, a photon does not experience time or space. According to relativity, as you approach the speed of light, time slows down for you. If you could reach the speed of light, time would stop completely. Space would contract to zero. This means that from the perspective of a photon, the moment it is created in the heart of a star and the moment it hits your eye, a million years later, happens simultaneously. For the photon, there is no journey, there is no distance. The emission and the absorption are the same event. This forces us to reconsider what we mean by particle. When we imagine a particle, we imagine a tiny ball traveling through the void. We imagine it having a little wristwatch ticking away the seconds of its journey, but the photon has no wristwatch. It has no internal experience of duration. In a very real sense, a photon is just a connection. It is a geometry of spacetime that links an electron in the sun to an electron in your retina. It is the mechanism by which charge talks to charge across the universe. The stuff it is made of is not matter, it is causality. It is the messenger that allows one part of the universe to affect another. So, where does this leave our definition? We have established that a photon is a discrete packet of energy. We know it behaves like a particle when it hits, but travels like a wave. We know it has zero rest mass, but carries momentum. We know it exists outside of the flow of time, but we are still describing its properties, not its substance. To get to the substance, we have to peel back another layer. We have to ask, if the photon is a ripple in the electromagnetic field, what is the field made of? Is the field just a mathematical grid, or is it a physical fluid? And how does this field decide to snap itself into a particle? This leads us into the realm of gauge theory. In modern physics, we classify particles by their spin. Electrons, protons, and neutrons are fermions, the building blocks of matter. They take up space. You cannot put two fermions in the same place at the same time. This is why the ground is solid. The electrons in your shoe push against the electrons in the floor. But photons are bosons. They have integer spin. They do not take up space. You can stack 1 billion photons in the exact same spot, and they won't mind. They are the force carriers. They are not the bricks. They are the mortar. In the next part of our investigation, we will dive into this distinction between matter and force. We will explore the idea that the photon is the gauge boson of the electromagnetic force. We will look at Richard Feynman's diagrams and see how photons are essentially the currency of the universe, exchanged between particles to tell them to move, spin, or bond. We are moving from the question of what is it made of to what is its job, and we will discover that without these massless ghosts exchanging information, the universe would instantly fall apart into a chaotic soup of isolated particles. The photon is the glue of reality. But to understand the glue, we first have to understand the spin. We have established that the photon is a contradiction wrapped in a paradox. It travels like a wave, hits like a particle, has no mass, and experiences no time. But to truly understand what a photon is made of, we have to stop looking at it in isolation. A photon does not exist to float alone in the void. It exists to facilitate relationships. It is the social worker of the universe. In the grand ecosystem of particle physics, there is a strict caste system that divides all reality into two families, the Fermions and the Bosons. Understanding this division is the key to understanding why light is so fundamentally different from matter. You are made of fermions. Electrons, protons, neutrons, and quarks are all fermions. The defining characteristic of a fermion is that it is antisocial. It zealously guards its personal space. This is codified in the Pauli exclusion principle, which states that no two fermions can occupy the exact same quantum state at the exact same time. They cannot be in the same place with the same energy and the same spin. This is not just a suggestion. It is the law that gives the universe structure. It is the reason you do not fall through the floor. The electrons in the atoms of your shoes push against the electrons in the atoms of the floor, not because they are touching, but because they refuse to occupy the same space. Fermions create volume. They create hardness. They are the bricks of reality. Photons are the opposite. They are bosons. Bosons are the force carriers, and they are fundamentally communal. They have no problem occupying the same space. In fact, they prefer it. You can pack an infinite number of photons into the same quantum state, overlapping them perfectly. When you do this, they act in unison, becoming a single, coherent superwave. We call this a laser. If fermions are bricks that stack on top of each other to build a wall, bosons are the ghosts that can walk through the wall and through each other without ever colliding. This is why two flashlight beams can cross each other without bouncing off. The light passes through the light because photons do not possess the exclusion property that defines solid matter. But what physical property dictates which family a particle belongs to? How does the universe know to make an electron a brick and a photon a ghost? The answer lies in a property called spin. When we ask what a photon is made of, a physicist might answer, it is made of spin 1. Now, we must be very careful here. When we say spin, our brains immediately picture a tiny basketball twirling on a finger. But quantum particles do not spin like basketballs. If an electron were actually spinning fast enough to generate its magnetic field, its surface would have to be moving faster than the speed of light, which is impossible. Quantum spin is not a mechanical rotation. It is an intrinsic form of angular momentum. It is a mathematical label that describes how the particle looks from different angles. To understand this, imagine a deck of cards. The ace of spades looks different if you turn it upside down. You have to rotate it a full 360 degrees to get it back to its original orientation. This is like a particle with spin 1. A photon is a spin 1 particle. If you rotate the universe 360 degrees around it, it returns to its original state. This seems normal. But fermions, like electrons, are spin 1, 2. This is where it gets weird. If you rotate an electron 360 degrees, it does not look the same. You have to rotate it another 360 degrees, a total of 720 degrees, to return it to its original state. It is as if the electron sees a universe that is twice as large as the one the photon sees. This mathematical difference in how they handle rotation is what creates the Pauli exclusion principle. Because the photon is spin 1, the math allows it to stack. Because the electron is spin 1, 2, the math forces it to stand apart. So, the stuff of a photon is partially defined by this specific geometric symmetry. It is a unit of spin, one angular momentum. This spin is not just a theoretical number, It is what allows the photon to do its job, and its job is to carry the electromagnetic force. This brings us to quantum electrodynamics, QED, the theory famously developed by Richard Feynman. In QED, forces are not magic pulls across a distance. They are the result of particles throwing things at each other. Imagine two ice skaters standing on a frictionless frozen lake. If one skater throws a heavy medicine ball to the other, the thrower will recoil backward. When the second skater catches the ball, the momentum of the ball will push them backward as well. They have moved apart. They have experienced a repulsive force. In the quantum world, that medicine ball is the photon. When two electrons approach each other, they don't just feel a repulsion, they exchange photons. One electron emits a photon and recoils. The other absorbs the photon and is pushed away. This exchange happens at the speed of light. But these are not normal photons. They are not the light you see with your eyes. They are virtual photons. This is a concept that blurs the line between existence and non-existence. A virtual photon is a temporary fluctuation. It exists on borrowed energy. Heisenberg's uncertainty principle allows a particle to pop into existence out of nothing, as long as it disappears quickly enough that the universe doesn't notice the energy debt. The heavier the debt, the faster it must vanish. Since photons have no mass, they can exist as virtual particles for quite a long time and travel long distances. So, when you stick a magnet to your refrigerator, what is happening? The magnet and the fridge are exchanging a blizzard of invisible, virtual photons. These photons are the stuff of the magnetic field. They are swarming back and forth, mediating the attraction. This completely redefines our question. A photon isn't just a beam of light traveling from the sun. That is a real photon, a ripple that has broken free and is traveling forever. But the universe is also filled with virtual photons that are tethered to matter, appearing and disappearing constantly to hold atoms together. The electric force that keeps your electrons orbiting your nucleus is a conversation made of virtual photons. This realization is profound. It means that the photon is the currency of interaction. It is the unit of exchange. Without photons, charged particles would be blind to each other. An electron would not know a proton was there. Atoms would not form. Chemistry would not happen. Light is the language that matter speaks. When an electron jumps from a high-energy orbit to a low one, it screams out a photon. That photon carries the information of that energy drop across the universe until it hits your eye, where it tells a molecule in your retina to change shape. The photon is made of information. It is a packet of news about the state of an electric charge. But this brings us to an even deeper layer of the onion. We have said that photons are excitations of the electromagnetic field. We have said they are spin-1 bosons. We have said they are the carriers of force. But what is the field? If you turn off all the lights, suck out all the air, and shield the room from all radiation, the electromagnetic field is still there. It is sitting at its zero energy state. But in quantum mechanics, zero is not nothing. The vacuum is not empty, it is seething with potential. The field is a fluid of probabilities that spans the entire cosmos. A photon is just a slap in that fluid. This suggests that the photon is not a separate entity from the universe. It is a feature of the background. It is a ripple in the fabric. When we ask what is a photon made of, we are really asking what is the vacuum made of, because the photon is just the vacuum ringing like a bell. In the next part of our investigation, we will descend into the vacuum. We will explore the zero-point energy and the terrifying realization that empty space has weight. We will look at how photons can spontaneously appear out of the darkness if you shake the nothingness hard enough. We are done with the particle. Now we must look at the stage it dances on. We have spent the last few segments talking about the photon as if it were an actor stepping onto a stage. We have described its costume massless, spin one, moving at the speed of light. We have described its role carrying the electromagnetic force between electrons, but we have largely ignored the stage itself. In classical thinking, the stage is just empty space. It is the void. It is what remains when you take everything else away. If you were to take a box and pump out every single atom of air, shield it from every cosmic ray, cool it to absolute zero, and block every photon from the sun, you would say the box is empty. You would call it a perfect vacuum. Intuitively, we believe that nothing is simple. It is the absence of something. But in the quest to find out what a photon is made of, we are forced to confront the most unsettling truth in all of quantum mechanics. There is no such thing as nothing. The vacuum is not empty. It is heavy, it is alive, and it is the fundamental substance from which all light is born. To understand this, we have to look at the electromagnetic field not as a smooth, static grid, but as a collection of springs. Imagine that every point in space, every tiny coordinate in the universe, contains a quantum harmonic oscillator. You can think of it like a pendulum or a guitar string. When a photon travels through space, it is basically a wave of energy, plucking these strings, passing the vibration from one to the next. But what happens when there is no photon? What happens when the light is off? According to classical physics, the strings should hang perfectly still, the energy should be zero. But quantum mechanics has a rule called the Heisenberg uncertainty principle. Most people know it as, you can't know position and momentum at the same time, but it also applies to energy and time. It says, you can never know the precise energy of a system for a specific slice of time with perfect accuracy. If the energy were exactly zero, we would know both the energy, zero, and the rate of change, zero, perfectly, which is forbidden. Therefore, the strings of the vacuum cannot stand still. Even in the deepest darkness, even at absolute zero, the electromagnetic field is jittering. It is vibrating with a zero-point energy. The vacuum is seething with activity. It is a bubbling ocean of half-formed particles, appearing and disappearing faster than reality can register. We call these virtual particles. In every cubic centimeter of empty space in front of your face, pairs of electrons and positrons and vast swarms of virtual photons are popping into existence, borrowing energy from the bank of the uncertainty principle, living for a fraction of a nanosecond, and then annihilating each other to pay the energy back. This is known as the quantum foam. This sounds like a hallucination. It sounds like a mathematical fiction invented to make the equations balance. But we know the quantum foam is real because we can physically feel it pushing against matter. In 1948, a Dutch physicist named Hendrik Casimir proposed an experiment to prove that nothing has force. He suggested taking two uncharged metal plates and placing them extremely close together in a vacuum micrometers apart. Classical physics says that since there is no charge and no gravity, the plates should hang there, indifferent to each other. But Casimir realized that by placing the plates so close together, you are restricting the vacuum between them. Think of the vacuum fluctuations as waves of all different sizes. Outside the plates, in the open universe, waves of any wavelength can exist: long waves, short waves, monster waves. But between the plates, only small waves that fit into the gap can exist. You have excluded the long waves. This means there is more vacuum activity outside the plates than inside. There is more quantum pressure pushing in than pushing out. The result? The plates are crushed together. The nothingness outside is stronger than the nothingness inside. This is the Casimir effect. It has been measured in the laboratory. We have seen metal plates pushed together by the sheer weight of empty space. This proves that the electromagnetic field is a physical medium. It is not just a concept, it is a fluid that fills the universe. So, what does this have to do with what a photon is made of? It tells us that a real photon, the light you see, is just an excitation of this background noise. Think of the vacuum as a calm ocean. The surface isn't perfectly glass smooth. There are tiny, microscopic jitters everywhere, the virtual photons. A real photon is what happens when you slap the water. You add enough energy to take one of those microscopic jitters and boost it up into a macroscopic wave that can travel across the ocean. A photon is a quantized excitation of the vacuum state. It is the moment the background hum screams out a note. But if a photon is just an energized piece of the vacuum, can we create light by simply shaking the vacuum? This brings us to a mind-bending concept called the dynamical Casimir effect. If the static Casimir effect comes from two plates sitting still, the dynamical version asks what happens if you move the mirror. Imagine a single mirror floating in the vacuum. It is being bombarded by virtual photons from all sides. They bounce off it and vanish. But if you accelerate that mirror to relativistic speeds, moving it close to the speed of light, something violent happens. The mirror moves so fast that it separates the virtual particles before they can annihilate. It rips the borrowed energy apart. It effectively kicks the virtual photons so hard that they gain enough energy to become real. This means that if you shake a box of nothingness fast enough, the box will begin to glow. You are not heating anything up. You are not turning on a bulb. You are converting the mechanical energy of the shaking directly into light by friction against the vacuum itself. In 2011, scientists at Chalmers University of Technology in Sweden finally managed to do this. They didn't move a physical mirror that's too heavy, but they used a superconducting circuit to simulate a mirror moving at 25% the speed of light, and they saw it. Out of the darkness, photons appeared. They created light from the void. This experiment gives us the most profound answer yet to our question. What is a photon made of? It is made of the vacuum. It is a piece of the fundamental fabric of spacetime that has been given enough energy to break free from the cycle of virtual birth and death. It is a permanent scar in the field. When you switch on a flashlight, you are not creating new stuff. You are simply whipping the existing quantum field into a frenzy, causing it to foam up into the real particles that we call light. The battery in your flashlight provides the energy to promote these fluctuations from virtual to real. This changes our view of the universe entirely. We used to think of the universe as a collection of particles moving through empty space. Now, we must view the universe as a solid block of fields. The empty space is actually the dense substance, and the particles, the photons, electrons, and quarks are just rare, energetic disturbances in that substance. We are not birds flying through the air. We are bubbles formed in a block of glass. The photon is not a stranger to the vacuum. It is the vacuum's song. However, this leads to a terrible problem. If the vacuum is so full of energy, if every point in space is vibrating with infinite harmonic oscillators, then empty space should be infinitely heavy. If you try to calculate the total energy density of the vacuum using quantum field theory, you get a number that is 120 orders of magnitude larger than the energy we actually observe. This is the vacuum catastrophe, the worst prediction in the history of physics. If the vacuum were truly that energetic, the universe would have collapsed into a black hole instantly, or ripped itself apart. But it hasn't. The vacuum seems distinctively lightweight. It is transparent. So, we are left with a split reality. Experiments like the Casimir effect prove the vacuum is full of energy, but the expansion of the universe suggests the vacuum is mostly empty. This contradiction suggests that there is something fundamental about the photon and its relationship to gravity that we do not understand. Does light weigh? Does the energy of the vacuum weigh? This forces us to look at the photon's interaction with the ultimate geometry, space-time. In the next part of our investigation, we will leave the quantum world and zoom out to the scale of Einstein's general relativity. We will watch a photon try to escape a black hole. We will ask, if a photon has no mass, why does it fall? Why is it trapped by gravity? We are going to explore the idea that light doesn't bend. The universe bends around it. The photon is the ruler by which we measure reality. But what happens when the ruler itself gets warped? We have spent a great deal of time dissecting the photon in the microscopic realm of quantum mechanics. We have looked at it as a packet of energy, a unit of spin, and a ripple in the vacuum. In all these descriptions, the defining characteristic of the photon has been its lack of mass. It is the ghost particle. It has zero rest mass, which allows it to travel at the universal speed limit and frees it from the passage of time. But this weightlessness creates a massive problem when we try to integrate the photon into the macroscopic world of gravity. According to the classical laws of Isaac Newton, gravity is a force of attraction between two masses. The equation is simple. The force equals the gravitational constant times the first mass times the second mass, divided by the distance squared. If you plug the mass of a photon, which is 0, into that equation, the result is 0. The force vanishes. According to Newton, light should be completely immune to gravity. A beam of light passing by a star should travel in a perfectly straight line, indifferent to the pull of the giant ball of gas. The universe should be a place where matter clumps together, but light sails on forever in Euclidean perfection. But when we look at the sky, that is not what we see. We see light bending. We see the background stars shifting their positions when the sun passes in front of them. We see entire galaxies acting as lenses, magnifying the light of objects behind them. Light does fall. It responds to gravity just as a rock does. This observation brings us to the most elegant and mind-bending realization about what a photon is. If it has no mass, gravity cannot be pulling on it. Therefore, gravity cannot be a force. This was the insight that led Albert Einstein to general relativity. He realized that the photon is not being deviated from its path. The path itself is curved. To understand the nature of the photon, we must understand the geometry of the road it travels on. Einstein reached this conclusion through one of his famous thought experiments. He imagined a physicist standing inside a sealed elevator, floating in deep space. If the elevator is motionless, a beam of light fired from one wall to the other travels in a straight line. Now, imagine a rocket is strapped to the bottom of the elevator, accelerating it upward. As the light beam crosses the room, the floor of the elevator moves up to meet it. To the physicist inside, It looks like the light beam is curving downward toward the floor. This is simple kinematics. But then, Einstein invoked the equivalence principle. There is no difference between acceleration and gravity. If you are standing in a sealed box, you cannot tell if you are sitting on Earth, feeling gravity, or being accelerated through space by a rocket. If acceleration bends light, then gravity must bend light. This means that when a photon passes by a massive object like the Sun, it is not being tugged by a force, it is simply trying to go straight. But the mass of the Sun has warped the fabric of space-time around it, creating a valley. The photon is like a marble rolling across a rubber sheet. It is following the straightest possible line through a curved environment. We call this path a geodesic. This fundamentally changes our definition of the photon. It is not just a particle moving through space. It is a tracer of geometry. It is the ultimate surveyor's tool. By watching where the light goes, we can map the invisible curvature of the universe. The photon is the only thing that reveals the shape of space. This relationship between light and gravity leads to phenomena that challenge our understanding of energy. Consider a photon trying to escape from the surface of the Earth. It is climbing out of a gravity well. If you throw a baseball upward, gravity pulls it back. The baseball loses kinetic energy and slows down until it stops and falls back. But a photon cannot slow down. It is defined by the speed of light, c. It must move at exactly 299,792,458 meters per second, no matter what. So, if gravity is stealing its energy as it climbs, but it cannot lose speed, what does it lose? It loses color. As a photon climbs out of a gravitational field, its frequency drops. Its wavelength stretches out. A blue photon becomes a green photon, then yellow, then red. We call this gravitational redshift. Conversely, if a photon falls into a gravity well, like light falling toward a black hole, it gains energy. It doesn't speed up, but it gets bluer. Its frequency screams higher and higher. This confirms what we suspected in the earlier parts of our investigation. The identity of a photon is entirely wrapped up in its frequency. It is a vibrating packet of time. Gravity affects it by dilating time. Near a massive object, time runs slower. Since frequency is just cycles per second, if the second gets longer, the frequency changes. The photon is a clock, and gravity changes the speed of the ticking. The ultimate test of this relationship is the black hole. A black hole is a region where the curvature of space-time becomes infinite. The valley becomes a bottomless pit. At a certain distance from the center, known as the event horizon, the escape velocity exceeds the speed of light. This is the point of no return. We often think of the event horizon as a physical barrier, but for a photon, it is simply a geometry trap. Inside the horizon, all future paths point inward. There is no direction you can point your flashlight that leads out. Space has been twisted so efficiently that out no longer exists as a direction. But strange things happen right at the edge. Just outside the event horizon, there is a region called the photon sphere. Here, gravity is so strong that light can actually orbit the black hole. If you were standing in the photon sphere, you could shine a flashlight at the back of your own head. The photons would circle the black hole and return to your eyes. In this place, light is trapped in a loop, endlessly retracing its steps. This creates a terrifying philosophical question about the information the photon carries. If a photon is a messenger carrying news of the universe, what happens when the messenger is imprisoned? When a photon crosses the event horizon, it is lost to us. The information it carries, its polarization, its frequency, its origin, is seemingly deleted from the observable universe. This leads to the black hole information paradox, a battleground where general relativity and quantum mechanics try to kill each other. Relativity says the photon is gone, swallowed by the singularity. Quantum mechanics says information cannot be destroyed. The wave function must vary unitarily. If the photon is truly destroyed, physics breaks. This paradox suggests that our understanding of what a photon is made of is still incomplete. We are missing a link between the geometry of the trap and the quantum nature of the prisoner. Some theories suggest that the photon doesn't actually fall in. The holographic principle argues that the information of the photon is plastered onto the surface of the event horizon, like a sticker on a suitcase. The 3D photon becomes a 2D piece of data encoded on the boundary of the black hole. If this is true, then a photon isn't a 3D object at all. It might be a projection from a 2D surface at the edge of the universe. We might be living in a hologram, and light is just the projection mechanism. This interaction with gravity proves that the photon is not separate from the fabric of reality. It is woven into it. Mass tells space how to curve. Space tells light how to move. And light tells us where the mass is. It is a closed loop. But there is one more twist to the story of gravity and light. We know that the universe is expanding. Space is stretching. And if space stretches, the photons traveling through it get stretched too. This is the cosmological redshift. The light from the Big Bang, the cosmic microwave background, has been traveling for 13.8 billion years. It started as blindingly hot gamma rays, but the expansion of space has stretched it 1,000 times over, turning it into cold microwaves. The photons have lost almost all their energy. Where did that energy go? When a baseball slows down, its energy goes into the air, or potential energy. But when a photon redshifts due to the expansion of the universe, the energy simply disappears. It is deleted. This violates the conservation of energy as we learn it in high school. But in general relativity, energy is not conserved on cosmic scales. The photon pays a tax to the expanding universe, and that payment vanishes into the void. This implies that the photon is a transient entity. It is born with energy, but the universe slowly drains it away until it fades into nothingness. So, we have seen that the photon is a slave to geometry. It follows the curves of space. It changes color as it climbs out of gravity wells, and it dies a slow death as the universe expands. But what happens when we try to use these photons to see the unseeable? What happens when we use light to look at the very thing that creates it, the atom? In the next part, we will shrink back down to the quantum scale. We will look at how an atom makes a photon. We will explore the quantum leap, the moment an electron teleports from one orbit to another and spits out a packet of light. We will ask, where was the photon before it was emitted? Was it hiding inside the electron? Or was it created from scratch? The answer will reveal that the photon is the sound of an electron changing its mind. We have spent much of our journey looking at the photon as a traveler. We have watched it streak across the cosmos, bend around black holes, and ripple through the vacuum. But every traveler has a home, and every journey has a beginning. To truly understand what a photon is, we must witness its birth. We must shrink ourselves down to the scale of the nanometer and enter the chaotic, buzzing machinery of the atom. This is where the magic happens. This is where the universe converts potential energy into light. If you look at the lamp beside you or the sun in the sky, You are seeing the result of countless trillions of microscopic catastrophes happening every second. A photon is not an eternal object. It is a creature of the moment, born from a sudden, violent change in the state of matter. To understand this birth, we have to update our mental picture of the atom. We are all taught the solar system model in school, where the nucleus is the sun and the electrons are little planets orbiting in neat circles. This model is useful, but it is a lie. If an electron were actually a little ball orbiting a nucleus, it would be constantly accelerating in a circle. Classical physics says that accelerating charges radiate energy. The electron would scream out X-rays, lose all its energy, and crash into the nucleus in a fraction of a second. Every atom in the universe would collapse instantly. Since we are still here, the electron must be doing something else. It is not orbiting, it is vibrating. In the quantum view, the electron is a standing wave. It is a cloud of probability that surrounds the nucleus like a fog. But this fog is not random, it has a shape. It can be a sphere, a dumbbell, or a donut. These shapes correspond to specific energy levels. The key is that the electron can only exist in these specific shapes. It is like a guitar string that can only play specific notes, an A, a C, or an F, but nothing in between. You cannot play a C and a half. The electron is quantized. It is locked into a discrete reality. So, how is a photon born? It happens when an electron gets tired. Imagine an electron is sitting in a high-energy shape, let's say, a large, vibrating dumbbell shape. It is excited, but nature is lazy. It always wants to go to the lowest possible energy state. The electron wants to relax down to a smaller, spherical shape near the nucleus. But there is a rule: conservation of energy. Energy cannot be destroyed. If the electron drops from the high shelf to the low shelf, the extra energy has to go somewhere. It cannot just vanish. The electron has to package that excess energy and throw it away. That package is the photon. This process is called the quantum leap, and it is one of the most mysterious events in physics. When the electron drops, it does not travel from the high orbit to the low orbit. It does not move through the space in between. It simply ceases to exist in the high state and instantly begins to exist in the low state. It teleports. In that exact moment of discontinuity, in that snap, where the universe resets the electron's address, the electromagnetic field ripples. A photon is created. It shoots out at the speed of light, carrying away the exact difference in energy between the two states. This is why atoms have unique fingerprints. A hydrogen atom has specific shells, so it can only produce photons of specific colors. Neon has different shelves, so it glows orange. The color of the light is the measurement of the fall. But here is the question that haunts us. Where was the photon before it was emitted? Was it hiding inside the electron like a coin in a pocket? No. The electron is a fundamental particle. It has no pockets. It has no internal structure to hide anything. The photon did not exist anywhere before the emission. It was created from scratch. It is similar to a spoken word. Where was the word hello before you said it? Was it hiding in your throat? No. The word was created by the action of your vocal cords interacting with the air. In the same way, the photon is created by the action of the electron interacting with the electromagnetic field. It is the sound of the electron changing its mind. There is a deeper layer to this mechanism. Why does the electron fall at all? If an electron is sitting in a high-energy state and there is no one pushing it, why doesn't it just stay there forever? A ball sitting on a flat table doesn't roll away unless you touch it. Why does the atom spontaneously decay? This phenomenon is called spontaneous emission, and for a long time it puzzled physicists. The answer brings us back to the vacuum we discussed in Part 5. The electron is never truly alone. It is surrounded by the vacuum fluctuations, the virtual photons popping in and out of existence. These virtual ghosts are constantly nudging the electron. They are tickling it. Eventually, a random fluctuation from the vacuum hits the electron just right and knocks it off its perch. It triggers the fall. This means that every photon emitted by every star and every light bulb is actually initiated by the invisible hand of the vacuum. The light we see is a collaboration between matter and the void, but we can also hack this process. If we don't want to wait for the vacuum to knock the electron down, we can do it ourselves. This is the secret of the laser. If an electron is primed and ready to fall, and we shoot a photon past it that has the exact same energy as the drop, the electron will resonate. The passing photon acts like a command. Drop now. The electron obeys and releases its own photon. But here is the miracle. The new photon is not just a random copy. It is a clone. It travels in the exact same direction, with the exact same frequency, and the exact same phase as the first photon. They march in lockstep. This is stimulated emission. It allows us to build an army of coherent photons, a beam of pure order. On the flip side of creation is destruction, absorption. This is how a photon dies. When light hits an atom, the process runs in reverse. If a photon hits an electron, and that photon carries the exact amount of energy needed to jump to a higher shelf, the electron eats it. The photon vanishes, and the electron teleports up to the excited state. This is why some materials are opaque and some are transparent. Glass is transparent because its electrons have no shelves that match the energy of visible light. The photons try to interact, but the electrons say, "Sorry, I can't use that amount of energy," and the light passes right through. Wood is opaque because its electrons have shelves that perfectly match the energy of visible light. They eat the photons and turn them into heat. This dance of emission and absorption is the heartbeat of the universe. It is how energy moves. The sun's core fuses protons, creating high-energy photons. These photons are absorbed and re-emitted by atoms inside the sun for 1,000,000 years, slowly losing energy until they reach the surface as visible light. They fly through space, hit a leaf on Earth, and are absorbed by a chlorophyll molecule, kicking an electron up a step to power photosynthesis. You eat the plant, and the energy becomes you. You are, in a very literal sense, powered by the ghosts of quantum leaps that happened inside a star. But there is a final, troubling implication to this story. We have described the photon as a discrete packet, effectively cut off from the source once it is launched. Once the bird leaves the nest, it is independent. But is it? Quantum mechanics suggests that particles that share a common origin remain linked in ways that defy space and time. If an atom emits 2 photons at once, or if one photon splits into 2, they are entangled. They are no longer 2 separate objects. They are one mathematical object stretched across space. This brings us to the edge of our understanding of reality. We have taken the photon apart, found it has no mass, found it is a ripple in the vacuum, and found it is born from the teleportation of electrons. But now we must ask, does the photon have an identity of its own, or is it just a shadow of a deeper connection? In the next part of our investigation, we will look at the phenomenon that Einstein called spooky action at a distance. We are going to explore quantum entanglement, we will see that two photons, separated by opposite ends of the galaxy, can instantaneously feel what happens to the other. We will ask if the speed of light is truly the speed limit of the universe, or if there is a secret backdoor that connects everything to everything else. We are about to learn that the universe might not be a collection of separate things, but a single, indivisible whole. We have arrived at the point in our investigation where the universe stops being polite and starts being impossible. Up until now, everything we have discussed about the photon, its wave-particle duality, its birth in the atom, its interaction with gravity has been strange, but at least it was local. Local is a very important word in physics. It means that things can only affect their immediate surroundings. If I want to push you, I have to touch you, or I have to throw a rock that travels through the space between us to hit you. A fire warms you because photons travel from the flame to your skin. The influence travels at a finite speed, respecting the cosmic speed limit of light. This is the comfort zone of reality. It implies that objects are separate entities, existing in their own little bubbles of space, independent of objects that are far away. But the photon is about to shatter this comfort zone. We are about to discover that under certain conditions, a photon does not have an independent identity. It can become inextricably merged with another photon, sharing a single soul across a vast distance. This is the phenomenon of quantum entanglement. To understand why this is so disturbing, imagine we perform a specific kind of alchemy. We shine a laser beam into a special kind of crystal, known as a non-linear crystal. Occasionally, a single high-energy ultraviolet photon will hit an atom in the crystal and split into two red photons, each with half the energy of the parent. These two red photons are born at the exact same instant from the same event. Because of the laws of conservation, they are linked. If the parent photon had zero spin, the two daughters must have spins that cancel each other out. If one is spinning up, the other must be spinning down. If one is polarized vertically, the other must be polarized horizontally. The universe demands that the ledger remains balanced. We take these two photons, let's call them photon A and photon B, and we send them in opposite directions. We send photon A to a laboratory in New York, and we send photon B to a laboratory in Paris. They are now separated by thousands of miles. According to our intuition, they are now two separate objects, like two baseballs thrown to opposite ends of a field. If I catch the baseball in New York, it has no effect on the baseball in Paris. But quantum mechanics tells a different story. It says that, until we measure them, neither photon has decided which way it is spinning. They are both in a state of superposition, a ghostly limbo where they are both spin up and spin down at the same time. Here is the magic trick. The moment the scientist in New York measures photon A and finds it is spin up, photon B in Paris instantly at that exact moment, with zero time delay, snaps into the state of spin down. It doesn't matter if they are separated by a room, a continent, or the entire visible universe. The decision of one determines the fate of the other. Albert Einstein hated this. He called it spooky action at a distance. It seemed to violate the one rule he held sacred: nothing travels faster than light. If the information traveled from New York to Paris instantly to tell photon B how to behave, it would have to break the speed of light. Einstein proposed a simpler solution. He argued that the photons weren't communicating faster than light. They were just pre-programmed. He used the analogy of a pair of gloves. If I put a left glove in a box and a right glove in another box and send them to opposite sides of the world, they are already defined. If I open my box and see a left glove, I instantly know the other one is a right glove. There is no magic communication. The information was there from the start. Einstein believed the photons carried hidden variables, secret instructions written inside them at birth that told them what to do. He believed reality was real even when we weren't looking at it. For decades, this was just a philosophical debate. Bohr said the properties were undecided. Einstein said they were hidden. But in 1964, a physicist named John Bell proved that this wasn't just philosophy, it was math. He derived a theorem known as Bell's inequality, which essentially said, if Einstein is right and the photons are like gloves with hidden instructions, there is a limit to how correlated their behavior can be. But if quantum mechanics is right and they are truly undecided until the measurement, the correlation will be stronger than that limit. Bell gave us a way to test the fabric of reality. In the 1,970 seconds and 80 seconds, and continuing to the Nobel Prize-winning experiments of 2022, physicists like Alain Aspect and Anton Zeilinger performed the test. They built the machines, they split the photons, they measured the correlations, and the results were unequivocal. Einstein was wrong. The gloves were not in the boxes. The hidden variables do not exist. The photons truly have no defined state until the measurement is made. The universe is not locally real. The correlation between the photons was stronger than any pre-programmed instruction could allow. This forces us to answer the question, what is a photon made of, in a radical new way? If two entangled photons act as a single unit regardless of distance, then distance might not mean what we think it means. For entangled particles, space is irrelevant. It is an illusion. We tend to think of the photon as a tiny dot moving through a vast, empty stage, but entanglement suggests that the stage is folded. At a fundamental level, photon A and photon B are touching. They have never separated. The concept of here and there dissolves. A photon is not a piece of matter located at a specific coordinate. It is a node in a network of relationships. Its identity is defined not by where it is, but by what it is connected to. This leads to the concept of quantum non-locality. It implies that the universe is holistic. You cannot break it down into separate Lego bricks without losing the essence of what it is. When we try to isolate a photon to ask what it is made of, we are like someone trying to understand a sentence by cutting out a single word and staring at it. The meaning is not in the word, it is in the context. The photon is made of its entanglement with the rest of the universe. However, we must be careful not to fall into mysticism. This instantaneous connection does not allow us to send text messages faster than light. We cannot use entanglement to communicate with aliens instantly. This is because the result of the measurement in New York is random. The scientist sees spin up, but he couldn't force it to be spin up. He just got a random result. The scientist in Paris sees spin down, which is also random to her. Only when they meet up later and compare their notebooks do they realize their random results were perfectly synchronized. Nature protects her speed limit by hiding the connection in the noise of randomness. We can share a secret, but we cannot send a signal. But there is an even stranger implication. If the state of the photon is created by the measurement, does that mean the photon requires an observer to exist? This brings us to the most controversial territory in physics, the measurement problem. When the photon is flying through space, it is a wave of probability. It is everywhere and nowhere. When it hits a detector, it becomes a particle. It becomes here. What causes that collapse? Is it the mechanical interaction with the atoms of the detector? Or is it the conscious act of knowing? Most physicists today stick to the decoherence theory, that the interaction with the chaotic environment forces the photon to choose a state. But the fact remains that the photon is a shapeshifter. It presents itself as a wave when we don't ask, "Where are you?" and it snaps into a particle when we do. This suggests that a photon is not a static object like a rock. It is a process. It is a potentiality that only hardens into reality when it interacts. It is like a render in a video game that only loads when the player looks at it. So, we have dismantled the idea that the photon is a localized object. We have seen that it can share an existence across the galaxy. We have seen that it defies the classical logic of separation. But if space is an illusion to the photon, what about time? If a photon can connect here and there instantly, can it also connect now and then? In the next part of our investigation, we are going to perform the ultimate magic trick. We are going to look at the delayed choice quantum eraser experiment. We are going to see evidence that a decision made in the present can seemingly affect the history of the past. We are going to ask if the photon knows the future, or if time itself is just another stubborn illusion that light ignores. We are about to enter the twilight zone of retrocausality. We have reached a point in our investigation where the ground beneath our feet is no longer solid. We have accepted that a photon has no mass, that it emerges from the vacuum, and that it can share a telepathic connection with a partner across the universe. These concepts are difficult, but they still fit within a framework of cause and effect. We generally assume that the past causes the present, and the present causes the future. We assume that time flows in one direction, like a river, and that events that have already happened are written in stone. But the photon does not respect our assumptions. In the strangest experiment ever devised by physicists, we have found evidence that the photon does not experience time linearly. It appears that a choice made in the future can determine the history of the past. If quantum entanglement broke our understanding of space, the delayed choice quantum eraser is about to break our understanding of time. To understand this, we have to go back to the classic double slit experiment. Remember the rule: if we put detectors at the slits to watch which path the photon takes, it behaves like a particle and creates two bands on the back screen. If we remove the detectors and let it pass unobserved, it behaves like a wave and creates an interference pattern of many bands. The act of measurement kills the wave. This seems to imply that the photon knows it is being watched at the moment it passes the slits. But in the late 1970 seconds, the physicist John Archibald Wheeler asked a provocative question: what if we delay the decision? What if we let the photon pass through the slits, travel through the air, and just before it hits the screen, then we decide whether to put the detectors in place? Does the photon have to go back in time to change its shape from a wave to a particle? Wheeler called this the delayed choice experiment. At the time, it was a thought experiment. But technology eventually caught up, and in 1999, a team led by Yoonho Kim performed the ultimate version of this test, the delayed choice quantum eraser. The setup is intricate, but the logic is terrifyingly simple. We start by firing a laser through a double slit. Inside the apparatus, we place a special crystal that splits every photon into an entangled pair. We call them the signal photon and the idler photon. They are born from the same event, so they share the same physics. We send the signal photon directly to a screen to be recorded. It has a short journey. It hits the screen and makes a dot. Its life is over. But the idler photon is sent on a much longer, more complicated journey through a maze of mirrors and detectors. This maze is designed to do one of two things. Depending on which detector the idler eventually hits, we will either know exactly which slit it came from, preserving the which path information, or we will scramble the information so completely that we can never know which slit it came from, erasing the information. Here is the crucial twist. The signal photon hits its screen before the idler photon completes its journey. The signal photon has already lived, died, and been recorded as a dot on a wall. Milliseconds later, the idler photon reaches the end of its maze and decides whether the path information is known or erased. If causality works the way we think it does, the idler's journey should not matter. The signal photon is already dead, its history is written, but that is not what happens. When the scientists looked at the data on the screen, they found something impossible. They looked at the dots made by the signal photons, whose partners later had their path information erased. Those dots formed a wave pattern. Then, they looked at the dots made by signal photons, whose partners later revealed their path. Those dots formed a particle clump. The signal photons, which had hit the screen in the past, seemingly knew what their partners were going to do in the future. It is as if the signal photon arrived at the screen and said, "I haven't decided whether to be a wave or a particle yet. I'm going to wait and see what happens to my brother in the maze 5 nanoseconds from now, and then I'll decide how I landed." This result sends a chill down the spine of anyone who believes in a linear timeline. How can an event in the future, the idler hitting a detector, influence an event in the past, the signal hitting the screen? Does the photon travel back in time? Does the universe rewrite history? The standard interpretation is perhaps even more disturbing than time travel. It suggests that history does not exist until it is recorded. The signal photon did not land as a wave or a particle. It landed as an undefined potentiality. It existed in a haze of probability. Only when the idler photon completed the circuit did the context of the universe solidify, locking the past event into a specific category. This brings us to the concept of the block universe. In this view, accepted by many relativistic physicists, the past, present, and future are all equally real. They exist simultaneously as a giant 4-dimensional block of space-time. The dinosaur extinction, the building of the pyramids, your birth, and your death are all just different coordinates in the block. We, as conscious observers, move through this block like a spotlight, illuminating one slice at a time, creating the illusion of flow. But the photon does not move through the block. It is a line drawn within the block. From the perspective of the block universe, the emission of the photon, its passage through the slits, and its detection are a single, unified geometric structure. The beginning and the end of the photon's path are connected. You cannot define one without the other. The delayed choice quantum eraser isn't magic. It's just revealing that the tail of the snake is connected to the head. But there is a catch, a safety mechanism that prevents us from using this to predict the future. If you were sitting at the screen watching the signal photons arrive one by one, you would not see a magic message appearing. You would just see a chaotic mess of dots. You would see a big, fuzzy blob. It is only after you get the data from the idler detectors and match them up, separating the erased partners from the known partners, that the hidden interference pattern emerges from the noise. You need the future information to decode the past, but you cannot see the pattern in the present. Nature scrambles the data just enough to stop us from building a time machine. We cannot send a winning lottery number back in time. We can only look back and realize that the lottery number was seemingly influenced by the future. So, what is a photon made of? In light of this experiment, a photon is not a little ball of energy that travels from minute to minute. It is a bridge that connects events in space-time. It is a thread of causality that can weave backwards and forwards. It tells us that the distinction between past and future is a persistent illusion of our biological minds, but it is not a fundamental constraint for light. The photon exists in a state where the question is the answer, and the answer creates the question. This leads us to the final existential confrontation. We have stripped the photon of its mass, its solidity, its independence, and now its place in time. We have peeled the onion until there is nothing left but abstract mathematics and geometric relationships. If a photon has no mass, no size, no time, and no fixed history, is it even a thing, or is it a glitch? Is it possible that light is not an object that exists in the universe, but rather the universe is a projection made of light? As we prepare for the final chapter of our journey, we must gather all these fragments: the energy, the field, the vacuum, the entanglement, and the time-traveling retrocausality, and try to build a final picture. We are going to look at the theory that suggests the photon might be the only thing that is truly real. We are going to explore the idea that matter, the heavy, solid stuff of our bodies, is just condensed light. We are going to ask if the universe is a hologram. In the next and final video, we will stop asking what the photon is made of and start asking what we are made of, and whether the answer has been shining in our eyes this whole time. We are heading for the grand unification. We have reached the end of our descent. We began this series with a question that seemed innocent enough to ask a child. What is a photon made of? We expected to find a recipe. We expected to find a list of ingredients, a microscopic blueprint that would tell us how the universe constructs a beam of light. But over the course of 9 nights, we have systematically dismantled every assumption we ever held about the nature of reality. We looked for a solid particle and found a wave. We looked for a continuous wave and found a discrete packet. We looked for mass and found a ghost that weighs nothing. We looked for a timeline and found a particle that exists outside of time, connecting the past and the future in a single, instantaneous stroke. We found that the photon is not a thing that exists in the universe. It is a vibration of the universe, a ripple in the underlying vacuum field that permeates every inch of existence. So, where does that leave us? If we strip away the mass, the time, the space, and the solidity, what is left? The final answer might be the most unsettling, yet the most beautiful concept in all of physics. It is the realization that the photon is not the exception to the rule of matter. It is likely the rule itself. We are not separate from the light. We are the light caught in a trap. To understand this, consider the most famous equation in history, E equals mc 2. Einstein taught us that energy, E, and mass, m, are the same thing, just in different forms. Mass is frozen energy. Energy is liberated mass. Since the photon is the carrier of pure electromagnetic energy, we can theoretically convert photons into matter. This is not science fiction. It is a prediction of quantum electrodynamics called the Bright-Wheeler process. It states that if you smash 2 high-energy photons together, 2 beams of light colliding in the void, they can annihilate each other and spontaneously birth an electron and a positron. Out of pure light, you get solid matter. You get particles that have mass, particles that take up space, particles that build atoms. This implies a profound truth. Matter is essentially condensed light. If you were to look deep enough inside the proton, past the quarks and the gluons, you would find a seething ocean of virtual particles, of fields interacting with fields. The mass of your body, the heaviness of your bones, and the solidity of your skin is not due to stuff inside you. It is due to the energy of the gluons binding your quarks and the photons binding your electrons. You are, in a very real physics sense, a collection of trapped energy fields. You are a box of light. Imagine a box with mirrors on the inside. If the box is empty, it weighs a certain amount. Now, imagine you shine a flashlight into that box and close the lid before the light escapes. The photons are bouncing back and forth inside, hitting the mirrors forever. Because the photons carry energy, and energy is equivalent to mass, that box is now heavier. If you put it on a scale, it would weigh more than the empty box. The stuff inside it is just light, but the effect is mass. This is a metaphor for the atom. The electron is bound to the nucleus by the exchange of photons. The quarks are bound by gluons, which are just strong force, photons. The solidity of the world is an illusion created by the furious motion of massless particles trapped in a dance. This leads us to the final definition of what a photon is made of. It is made of information. In the modern view of the universe, emerging from theories like the holographic principle and string theory, the universe is fundamentally a data processing system. The photon is the bit. It is the smallest unit of communication. It is the signal that tells an electron to move, a chemical bond to form, or a neuron to fire. Without the photon, the universe would be static. It would be a collection of isolated islands, unable to touch, unable to see, unable to change. The photon is the agent of causality. It is the verb of the universe. When we look at the night sky, we are not looking at a collection of objects. We are looking at a conversation. The stars are speaking to us across the void, and the words they speak are photons. Every photon that hits your eye carries a history. It carries the signature of the hydrogen atom that birthed it. It carries the redshift of the expanding cosmos. It carries the polarization of the magnetic fields it passed through. It is a zip file containing the story of its journey, and when it hits your retina, it unzips. It transfers that information to your brain, allowing you to reconstruct a picture of reality. But here is the irony. The photon itself experiences none of this. Because it travels at the speed of light, its clock is stopped. For the photon, the journey is instantaneous. It is born in the star and dies in your eye in the same moment. It connects the emitter and the absorber into a single quantum event. This suggests that at the fundamental level, separation is an illusion. The star and your eye are touching. The sun and the leaf are touching. The photon is the thread that stitches the fabric of space-time together, pulling distant points into contact. So, if you ask me one last time, what is a photon made of? I will tell you this. It is made of the possibility of interaction. It is the universe acknowledging itself. It is the ghost that arises from the vacuum to say, something is happening here. It is the bridge between the nothingness of the void and the somethingness of matter. We started this journey looking for a mechanical explanation, like a watchmaker taking apart a clock. We end it as mystics, standing before a mystery that mathematics can describe but language cannot capture. We have found that the solid world is mostly empty space, and that empty space is full of energy. and that the light which illuminates it all is a timeless, massless, shapeless flicker in a quantum field. We have learned that we are made of the same fields, just vibrating at a different frequency. We are the light that has learned to slow down, to circle, to knot itself into form, and finally, to open its eyes and look back at the source. As we close the doors of the Still Science Lab tonight, take a moment to look at the light bulb in your room. Do not see it as a simple appliance. See it as a machine that is agitating the vacuum of the universe. See the photons streaming from it, not as tiny bullets, but as ripples in an infinite ocean, carrying energy from the power plant to your skin. And realize that the only reason you can see it, the only reason you can feel it, and the only reason you exist to think about it is because of the massless ghost we call the photon. It is the messenger, the message, and the medium all at once. Thank you for joining me on this 10-part deep dive into the quantum realm. We have traveled from the classical mechanics of Newton to the event horizon of a black hole, and finally to the very structure of our own existence. There are many more mysteries to explore in this universe: dark matter, the nature of time, the origin of consciousness. But for now, we will let the photons rest. The lab is closing down, the lights are dimming, returning the vacuum to its quiet hum. Good night, and I will see you in the next video.